Greetings. So, in our previous classes we have discussed mostly the semi-empirical formulation of electrodynamics. Semi-empirical is what is based on empirical laws, empirical observations in experiments, carefully done experiments, once, twice, 10 times, 100 times, thousands of times. Take two charges, take a small charge and a big charge, then a big charge and a big charge, then a big charge and a small charge, and change their values. Keep them at this distance, keep them at this distance, at this distance. Estimate the force, and no matter what charges you are using, no matter how far you set them up, the force is always Q1, Q2 by the distance square. Now, when you arrive at this conclusion by carrying out these observations, you have an empirical law. Okay? So, this is how the laws of electrodynamics were formulated by Coulomb, Gauss, Ampere, Faraday, Lens, okay, Ohm, Kirchhoff, Henry, all right, who also comes in the same league as Faraday and Lens, the same set of experiments. And then from this semi-empirical formulation, you come up with a theoretical model which sort of provides an umbrella for all of these laws. They come together. They come together in the theory of Maxwell. And until then, it seemed as if there were separate laws for electricity and for magnetism. So, these were pursued as two different disciplines, and then Maxwell recognized that these are not really separate disciplines, and this was the first unified field theory. This was a field theory because the idea of field was properly given a formal structure in Maxwell's theory, although there were some suggestions about a field theory in various earlier attempts, including from those which go back to the times of Kepler and Newton, which I mentioned earlier. And then in the work of Lagrange and Euler, who worked with the velocity fields in fluids. But then the velocity fields also required the material particles of the fluid to move, whereas in the theory of electrodynamics, you do not have material particles, but you just have the idea of fields. And then this idea continues to be developed even today. You have got the quantum fields, you have got the Higgs field, and it is a continuing theory. So we were set on this path by Maxwell, and we will see this unification. And the idea to develop an umbrella theory is to be able to, the primary objective of course is to understand physical observations and then also be able to make predictions. And these predictions are important because if the theory can make predictions which are verified in the laboratory, then of course the theory is correct. In case a single experiment is done anywhere in the world which is not consistent with a theory, then you have to correct the theory, you have to modify it, and sometimes you even have to replace it, which is how the non-relativistic theory had to be replaced by the relativistic theory. The classical mechanics has to be replaced by quantum mechanics and so on, right? So you have to do that. It does not mean that the theories which are replaced are totally incorrect and not worth learning. They are very much worth learning because they provide excellent approximations to the correct theories. That is number one. And they also help us build the vocabulary and build the concepts in our minds, which continue to remain important as you replace these theories by more appropriate theories, including the quantum and relativistic theories. So classical mechanics is extremely important. It's not something that you learn and then dismiss by saying that, okay, this is not correct anyway. It's not like that. It provides the whole framework of understanding quantum theory, which takes you beyond the classical ideas to more accurate explanations, which become absolutely necessary in several situations. So, what we have so far learned, let me quickly revisit some of these ideas. We have seen these laws to operate in steady state electromagnetism, right? Steady state when the physical quantities do not change with time, all right? And I include things like what happens when you place a conductor in an electric field, because sure enough there is a reorganization of charges, and that takes place over a passage of time, obviously, because the charges have to move around. That takes time, but the time is so short that we are not considering what happens during that extremely tiny time interval. We have discussed phenomena which take place after the equilibrium is quickly attained, after the reorganization is attained, and then we have a steady state, all right. So, it is this steady state electromagnetism that we have discussed, and you have got these relations both in the differential form and also in the integral form, which are completely equivalent to this, to the differential form. And we can use things like the Kelvin-Stokes theorem to write the surface integrals as line integrals and so on. So, all of these things are known to you, and this is what we have discussed early on. So, these are the equations which eventually get incorporated in Maxwell's equations, but Maxwell's equations are more than this, as you will see. You also need to know how matter responds to fields. So, there is some stimulus response mechanism which exists, and this is contained in what are known as constitutive relations, which are a separate set of laws separate from Maxwell's equations. Maxwell's equations give you the divergence and the curl of E and B. In addition to this, to be able to do electrodynamics, you need the constitutive relations, and J equal to sigma E, the Lorenz Force Law is one of those, right. This is the stimulus response or the cause effect kind of relationship, and this is why Feynman calls it as Newton's law of electricity, not in the sense that it accounts for change in equilibrium, but it accounts for what happens when there is a certain stimulus. So, when there is a voltage difference, a current is set up, okay. So, V equal to I times R, which is the Ohm's law, is a stimulus response mechanism, that you have a voltage difference which is V, and that is responsible for setting up the current which is I, and the relationship between them is V is equal to IR. So, this is a stimulus response kind of relationship, which is why Feynman calls it as Newton's law of electricity. So, this is the Ohm's law, and obviously you have a DC circuit in this. So, you have got a battery, and in this circuit over here you will have the Ohm's law to be valid. You also have the Kirchhoff's laws, all right, which tell you that the sum of the currents at a node go to 0, and that the sum of the voltages in a closed loop also goes to 0. So, that takes care of the polarity of the source of battery and the differential voltage which is responsible for the passage of a current. Okay, so, these are the two Kirchhoff's laws. If you think about the Kirchhoff's law in an inverse manner, you recognize that if there is no source of battery, there would be no current. Okay? If there is no chemical reaction which is driving the currents. So, in the battery you have got a chemical reaction, as a result of which there is a passage of the ions in the battery, right. And I am using the terminology which belong to the time of the experiments in electricity which were done by Ohm and Kirchhoff, right? If there is no battery, there would be no current. Now, if you look at this circuit in which you have got a closed circuit, you have got an ammeter which senses a current. The ammeter would kick if there is a current flowing in it, and you place this circuit in a region of magnetic field which is the shaded area in this figure, and the direction of the magnetic field is into the plane of the figure. So, you see the tail of the arrow, all right, and you do not expect any current to flow in this because there is no source of battery, okay, and sure enough the needle does not deflect. So, this is what we would expect, and this is what happens. If you do the same experiment in which you have the segment PQ in this figure to be movable. So, you have got a movable contact at point P and a movable contact at point Q, and this wire you move from left to right. That is what is shown by this arrow over here. You can move it toward the left as well, but I am considering a movement toward the right. And if you move it to the right, then what is going to happen is that a charge in the segment PQ is going to be dragged to the right. So, it picks up a velocity to the right, and then it will be forced to move in the direction of V cross B. And because it is forced to move in the direction of V cross B, a current is set up, okay, and the ammeter kicks in. Now, this is really amazing because on the bottom right of this you have got the Kirchhoff's law, which tells you that if there is no voltage source, that if there is no battery, there cannot be any current. And now we do not have any battery, but we do have a current, and we are able to account for it by invoking the constitutive relation, which is the Lorenz force. Okay? So, now we do another experiment in which we will not move the circuit. So, this particular source of voltage difference that we just now talked about is an electromotive force. It is really not a force because it is the voltage difference delta V which makes a current flow in the circuit, like V is equal to IR in the stimulus response, Newton's law of electricity spirit, right. In that sense of the term, it is the voltage differential which is really the work done E dot dl in carrying a unit charge from point A to point B. It is actually work done, it is work, it is energy difference and not really a force. It will not have the dimensions of force. The dimensions of force are the dimensions of dP by dt, right, which is mL t to the minus 2, right, dP by dt, whereas this is delta V, it will have the dimensions of work done. So, it is really not a force, but it is called as a force in the sense that okay, it makes something happen, and that is the way this term was used and it has got stuck. So, it is called as motional EMF. Why? Because the motion of the circuit element PQ is involved in this, all right. In the next experiment, we are not going to move the segment PQ, but we are dragging the field itself to the left, and once again the ammeter needle is seen to kick. Now again, From Kirchhoff's law, we should know that there being no voltage source like a battery in the circuit, we do not expect any current. The charge elements in the segment P to Q are at rest. So, they cannot experience any Lorenz force V cross P, okay? Because Lorenz force requires the charge element to be moving so that velocity is not 0. And now you cannot expect any current at all, but you do see it. This was seen in the experiments done by Faraday and Lens and Henry, okay? So, this was seen, and you need a different explanation. So, again you must have a certain voltage differential which must be driving this current, right. So, a similar cause effect relationship for which you will need to invoke some mechanism, and this mechanism is what you would call as electromotive force, although we know now that it is really not a force, but we have accepted the term for our general usage. So, this is another source of EMF, which is not because of the Lorenz force, but it is because the magnetic flux which is crossing the circuit is changing, okay? And it is the rate of change of the magnetic field in that area which is responsible for this. So, this also generates an EMF, and you call it by the same name because it results in the same phenomenon that a current is set up. So, this is again neither due to the battery nor due to the Lorenz Force Law, but it is coming from a completely different mechanism, okay? And now as a result of this, you can see immediately, because this line integral E dot dl does not go to 0, okay? And this line integral is nothing but equal to the surface integral of curl of E, right. And if you now look at these two sides of the equation, then you find that the electric intensity field is not irrotational, but it is equal to minus del B by del T, because the integrands of the two surface integrals have to be exactly equal. They are definite integrals over exactly the same surface, okay. Not only that, if you neither move the field nor the circuit, you still have the same result. If you change the magnetic field as a function of time, you have got some mechanism, you may have an electromagnetic magnet, all right, or you may generate a magnetic field between two poles of a bar magnet and you move them around, right, and you can do it in so many different ways. And if you change the value of the magnetic field and move neither the circuit element nor the magnetic field itself, neither the position of the magnetic field, but you just change its magnitude, even then you have an EMF which is set up, which is again called as EMF because it has the same result, okay. So, it is a changing magnitude of the magnetic field which is responsible for this, and that also generates an EMF. So, now you have got these two amazing situations, one on the left half of this figure and the other on the right half of this figure. On the left half you have to invoke the Lorenz Force Law, and on the right you are invoking the Faraday Lens empirical law, okay. And as I mentioned in an earlier discussion, Feynman exclaims that no other place in physics, there is no other place in physics where such a simple and accurate general principle requires for its real understanding an analysis in terms of two different phenomena. The two phenomena are completely different. One is the Lorenz force, in which a charge must have a certain velocity, without which it cannot encounter this force. The other is a force rather there is a voltage difference which pops up on account of the changing magnetic field, and this changing magnetic field results in a potential difference, and that potential difference is what drives the current. So, these are completely two different phenomena, and you have the Faraday Lens Maxwell law that there is an EMF which is set up, which is given by this E dot delta L, right, which is the energy required to move a charge over a closed loop, a unit charge over a closed loop, and you can write this as a surface integral as well. And this law is valid for any kind of circuit element. It does not have to be just a rectangular circuit that we considered in the previous example, but it can be a circuit of any arbitrary size and shape as long as it is a closed loop. You just take a conducting wire, all right, and move it in a magnetic field, and the magnetic field can have any kind of orientation. It has got a parallel component which is in the plane of the figure and an orthogonal component which is perpendicular to the plane of the figure. No matter what direction the magnetic field has, if you just take a closed wire and move it in a magnetic field, a current is set up in that. Okay? Now, this is really amazing, and this is similar to the Ampere's law in one sense. Ampere's law, we saw that the curl of the field B is equal to mu 0 times J. We showed it first for an infinite straight wire, and then we took the Biot-Savart law and arrived at the same result no matter what the shape and size of the current was. It did not have to be an infinite straight wire. Okay? So, for any arbitrary geometry, now this is what makes it a law. If it is valid for just one particular case of infinite straight wire, it is not really a law. But then if it is valid for no matter what is the shape and size of the current loop, then it becomes a law, because you can apply to everything else. Like Coulomb's law becomes a law not just because you have two equal charges of the same magnitude, you may have unequal magnitudes, unequal signs, but the law is the same, which is that the force goes as Q1 Q2 by distance square, right. So, it becomes a law when it is general. So, the generality is an essential feature of any law, and this is why the Biot-Savart Maxwell law becomes a law, and these are valid for any geometries. So, we will quickly convince ourselves that this Faraday Lens law, or which we will incorporate in the scheme of Maxwell's equations, is a general law. So, we take a circuit element which is around this, all right, and there is this, it encloses a certain surface which is shown by this patch, yellow patch, right, and we move this orthogonal to the plane of the figure into the plane of the figure, right. So, you will see the tail of its movement, right, which is shown by this cross arrow, right, and it is moving in a region where there is a magnetic field which has got some arbitrary direction, it does not matter, but whatever its direction is, you can always break it up into a component which is parallel to the plane of the figure and another which is orthogonal to it, right. You can just decompose the vector, and you have this movement of the circuit element, and then ask what is going to happen. So, what happens is, we can figure out what is going to happen if we consider what we already know so far, that what we are going to do is to consider a ribbon between the two positions of the moving surface. So, you have got the surface which is in front of the plane of the figure and another position of the another orientation of the circuit element when it has gone through the plane of the figure and goes to its backside, right. So, those are the two positions, and between these two positions there is a ribbon which encloses it. So, it is just a mathematical surface, all right. It is not a physical surface, it is just a mathematical surface, and that is what I am referring to as a ribbon. So, this circuit is moved at a velocity v. So, it crosses the distance v into delta t, all right. And if you take a small strip on this ribbon, it has got a dimension delta L, which is shaded in red. So, that is the geometry we are considering, right. It is mostly mathematical objects. The only physical thing over there is this closed wire loop and the magnetic field in which it is moving. Everything else is just mathematics. So, the flux which crosses the current element at the time t is B dot ds, and B dot ds must be evaluated at a later time t plus delta t to get the flux which is crossed at a later time, right. So, now since we know that there are no magnetic monopoles, right, the divergence of B goes to 0. So, its volume integral goes to 0, and the volume integral of the divergence is the same as the surface integral B dot ds. So, that also goes to 0. So, if we now apply this relationship to the surface which is enclosed by the front surface, which is the yellow patch when the movement begins, and the rear patch after time delta t, and the surface becomes closed by considering the ribbon which surrounds it. So, we now evaluate the surface integral over the closed surface which I just mentioned. So, you add up the surface integrals over the flat face at time t, add over the B dot ds on the surface of the ribbon, and then add the surface integral B dot ds at a time t plus delta t. This must vanish, right. Okay. And what does it mean? That this part and this part must be equal and opposite, because the unit normals to those surfaces are exactly opposite, and if you go infinitesimally close to that, right, you will have just the opposite contributions. So, those contributions cancel each other, and the difference between the flux at t plus delta t and t itself is given by nothing but B dot delta s, and delta s, if you just consider the portion shaded in that red strip, that is the small part of the ribbon. So, over this it is V delta t into delta L. So, that is the area of that shaded part, which is one side multiplied, which is V delta t, multiplied by the other, which is delta L. So, now you have got a very straightforward relationship that if you divide both sides by delta t, then you have got delta phi by delta t, which is equal to B cross V dot delta L. If you take the reverse of the cross product, instead of B cross V, you take V cross B, you get a minus sign, and minus V cross B is nothing but the Lorenz force per unit charge. Okay? So, that is what you get, minus of F dot delta L. So, minus of F dot delta L is like the EMF that you get, right. And if V is the velocity of the wire, and on that wire you have got a charge which is flowing along the direction of the conductor itself, then its net velocity is the sum of the two. Okay. So, this velocity you break up between the component W and component U and take the difference. However, U is parallel to delta L. So, the dot product, scalar product of 3 vectors, 2 of which are parallel, vanishes, and you are left with only the residual component. So, you get delta phi by delta t, which is minus w cross b dot delta L. So, that is the expression you get for the EMF. Okay? And this result is what gives you the Faraday lens expression. Okay? And we see that this is valid for any arbitrary shape. It does not have to be a rectangular loop or any particular direction of the magnetic field which is orthogonal to it. You can have the loop even twisted, it does not have to be in a flat plane. You can bend it, all right, and you will have the same law which is valid. And because it sets up a current, you must identify the cause of this phenomenon to a voltage difference, because we know that a voltage difference is required to set up a current, right. So, this cause is what you call as the EMF, and this is the motional EMF. It is not a force, it is a potential difference. Okay? So, this is the Faraday Lens law. So, these are valid for every general case. It is not valid just for a particular geometry. This is the point that I was emphasizing, and that is really what makes it a law. And we now have, we can accommodate this in our expression. So, first we had these relationships for steady state electromagnetism, and now we have got a phenomenon which is coming from time dependent magnetic field. So, the curl E is no longer equal to 0. It is equal to 0 if B is independent of time, but not otherwise. Okay? So, del cross E equal to 0 now becomes a subset of a larger equation, which is del cross E equal to minus del B by del T. The first relation is not wrong, it is a special case of the second. When B is independent of time, you recover the previous case. So, steady state electromagnetism is an integral part of time dependent electromagnetism. Okay? But the expression has to be modified. So, from del cross E equal to 0, Maxwell modifies it to del cross E equal to minus del B by del T. Okay? Now, you have got the curl of B equal to mu 0 J. This is the Ampere's law. We have convinced ourselves that it holds for an infinite wire. We have also convinced ourselves that it holds for a current in any closed circuit, no matter what its shape is, no matter what its size is, whether it is in a plane or it is twisted, as long as you have got a current flowing, then the curl of the magnetic field is always equal to mu 0 J. But if that is true, then its divergence must go to 0, right, because this is a vector identity that no matter what vector field you are talking about, okay, if it has got continuous derivatives, then its divergence of the curl must go to 0. So, now you have got two expressions for curl, one for curl of E and the other for curl of B. So, let us check if the divergence of both of these equations, both of these curls go to 0. So, let us check the curl, the divergence of the curl of E. So, the divergence of the curl of E becomes the divergence of B, because the divergence and the time derivative operators commute, they are completely independent, and the divergence of B is 0. We know that there are no magnetic monopoles, and therefore, there is no problem here. What about the divergence of the curl of B? So, the divergence of the curl of B becomes mu 0 times divergence of J, but divergence of J from the equation of continuity that we have studied in fluid mechanics, which is also valid for the conservation of charges when charges are in motion, and we discussed that in the context of fluid mechanics, right. So, del dot J plus del rho by del T goes to 0 for charge flow as well, and therefore del dot J will be 0 only if rho is not changing with time in steady state, not otherwise, which means that the divergence of the curl of B is not guaranteed to be 0. But vector calculus tells us that the divergence of the curl of B must always be 0. So now we have a conflict. How do we resolve it? And this is where Maxwell took a bold step. He said that vector calculus is always correct because those are general theorems. They must be valid for any vector field, and if it is valid for any vector field, then it has to be valid for the curl of B as well. The divergence of the curl of B must vanish. And what is not making it vanish is that the divergence of J is minus del rho by del T. So curl of B cannot be given simply by mu 0 J. There must be a compensating term which will kill this. Okay? So he proposed that the divergence of curl of B, he finds what the divergence of the curl of B is, okay, and introduces this corrective term that the curl of B cannot be given by just mu 0 J, but by mu 0 J plus a time dependent term. Because when you take the curl, the divergence of this, the divergence of the second term will happily cancel the divergence of the first term. And then you have no conflict with vector calculus. So the power of mathematics is really driving discovery of the laws of physics. This is amazing. You learn new laws not just by doing experiments, but inspired by your faith in mathematics, that I know for a fact that the divergence of a curl must always be 0, that cannot be wrong. Therefore, the physical law cannot be simply that the curl of B is equal to mu 0 J, but it must be curl of B equal to mu 0 J plus mu 0 epsilon 0 del E by del T, whose divergence will cancel the divergence of the previous term. So this is incorporated in Maxwell's theory, and we now take this discussion forward. So we have this understanding of the voltage difference which sets up the current, which is the cause-effect relationship in the sense that Feynman calls this as Newton's law of electricity, right? So you have got a voltage difference, which is what the EMF is. It is not a force, it is a voltage difference, and it results in, it can be generated through changing magnetic flux, which is time dependent, and it sets up a current, right? So similar to this, you have an Ohm's law of magnetism, because a flux is the result of a current, right? If you have a current, then it results in magnetic flux. So just like if you have a voltage difference, you have got a current flowing. If you have a current flowing, you have got a magnetic flux. And there is a law that you can write in complete analogy with the Ohm's law, that F is equal to phi times R, where R is called as the reluctance. This is the script R. It has got a similar structure as the resistance in the electric circuit. So this is the script R will have the same role in magnetic circuits or in magnetic circuit elements. So this was proposed by Henry Rowland, but it is often called as Hopkinson's law, but it was proposed prior to Hopkinson, and in fact Hopkinson refers to this as Rowland's contribution. So this is the Newton's law of magnetism, if you wish, or Ohm's law of magnetism if you wish, all right. And this is a phenomenon which is similar to what is responsible for the flow of a current, but in magnetism it is responsible for the generation of a magnetic flux, and this is in analogy called as the magnetomotive force, MMF. This is the magnetomotive force. So, this magnetomotive force, as you can see, it is essentially current, all right. So, when you have a current, it sets up a magnetic field. So, that is the cause effect kind of relationship that we have over here, and notice that we reinterpret this, that okay, what is it that sets up a magnetic field? Whatever that sets up a magnetic field is what you can call as a current. Like whatever was responsible for the flow of charge is what you call as voltage difference. So, in the older days it was the DC battery which was generating that voltage difference, but then in the Faraday Lens Henry scheme it is a changing magnetic field which is again called as a voltage difference, and that voltage difference is what we call as EMF. So, now our idea of MMF, the magnetomotive force, is going to be anything that sets up magnetic flux. It can be a current, it can be anything else that sets up the magnetic flux. Okay? So, you can have a magnetic flux from a current, you can also have it from a changing electric field, right. And just the way you could have electric fields from changing magnetic fields, you can have a magnetic field from changing electric fields. So, there is a symmetry which is driving this consideration. Okay? So, now you have another source of magnetic flux which is the change in the electric flux. Not just the conventional current which is generated by a source of a chemical reaction in a battery, but a changing electric field, changing electric flux can also generate a current, and you can attribute this to a magnetomotive force. Okay? In the next class, we will also introduce that there is a third source of magnetic field. There is intrinsic quantum magnetic moment which is associated. I think this M is lost, let me fix it. Oh, it is gone behind this, I think, so let me bring this to the front. I don't know where it is lost. There should be an M here. Okay? So, you have got this quantum magnetic moment which also generates magnetic fields, all right, and this is something that we will talk about in the next class. But given all of this, we recognize what magnetomotive force is. So, this is really not a force in the same sense, okay, but it is in the sense that it is what generates a magnetic flux, just as an electric current, the conventional current does. So, in that sense it is a magnetomotive force. And notice that there is a length element. So, we will be interested in magnetomotive force per unit length, and that is where we will introduce the idea of magnetic intensity. We will introduce that very shortly, all right. So, you have got, if you look at the Ohm's law for electricity and the Ohm's law for magnetism, both have got the same forms, both have got an element R which is resistance in the case of Ohm's law for electricity, and you have got the reluctance in the Ohm's law for magnetism, and both depend on length, which is why you will have to determine the corresponding quantity per unit length, all right. And that is what will lead to the idea of H as opposed to B, and these two are different things. So, one is called as the magnetic induction field, the other is sometimes called as the magnetic intensity or the magnetic field strength. And in fact, the book that all of us use extensively for these topics is the book on electrodynamics by Griffiths. Griffiths prefers to just call it as H. He doesn't like to give it any different name, and he uses field for B. Okay? So, you have to be a little careful with the terminology, and you have this idea of magnetomotive force, which is essentially a current, okay. But if you are generating a magnetic field by something like a solenoid, you take a wire and you send a current through it, then the magnetic field that is generated inside it will depend on the number of turns, which is why this is often measured in terms of ampere turns, okay, because it is the current which is generating, which is the source of the magnetic flux which is generated. Okay. So, this is the this is what sets up a magnetic flux, and now these laws are modified. So, the curl of E equal to 0 is replaced by curl of E equal to minus del B by del T. So, of which the previous case becomes a special case. Likewise, the curl of B equal to mu 0 J also becomes a special case of a more general expression, which is mu 0 J plus mu 0 epsilon 0 del E by del T. And this is a very bold and correct step, because now it does not leave any inconsistency with vector calculus, right. So, this is a modification of the Ampere's law by Maxwell, and you notice that there is a certain symmetry in the two relations. There is also some asymmetry. So, see what you can learn from the symmetry and see what you can learn from the asymmetry, right. So, first of all, there is an asymmetry here, that the divergence of the electric field may be 0, but it may also not be 0. It is in general rho over epsilon 0, whereas the divergence of the magnetic field is always 0. So, the asymmetry suggests that there are no magnetic monopoles, but Maxwell's equations will remain valid and intact even if you presume that divergence of B is not equal to 0. That will require you to discover a magnetic monopole. So, good luck for that. If you do that, yes, you will be a big name in physics, right. And Maxwell's equations do not prevent you from attempting that. Okay. There is another asymmetry, that there is a minus sign in the curl of E and a plus sign in the curl of B. Now, that comes from the fact that E and B are different types of vectors. How do they, what is a vector? A vector is defined by how its components transform. How its components transform when you rotate a coordinate system and when you reflect a coordinate system. Okay? So, E and B are different kinds of vectors. E is a polar vector, B is an axial vector. B is an axial vector, it is a pseudo vector, it is something like angular momentum. There are other pseudo vectors, like angular momentum, torque, there is the magnetic field, there is a magnetic moment, okay? The surface area elements, okay? These are all axial vectors. And this asymmetry is because of the different nature of these two types of vectors. In vacuum, J will be 0, rho will be 0, and the equations take a simple form. But in vacuum also, if there are time dependent variations in electric field and magnetic field, then of course the curl of E is not 0 and the curl of B is also not 0. Okay? What you have in front of you are the divergence and the curl of the electromagnetic fields. So look at the two equations, divergence of E and the divergence of B. And now you have the curl of E and the curl of B. Now this is amazing, because the divergence and curl of a vector field are extremely important physical quantities. If you know the divergence and curl, you can get what that vector field is precisely if you also know some boundary conditions. Okay? And how a charge responds to an electromagnetic field is given by E and B. F is equal to charge times E plus V cross B. So the whole dynamics is contained in this response theory. And to study dynamics, you need E and B, and you can get them from Maxwell's equations, but you also need the boundary conditions. So this is contained in what is called as the uniqueness theorem, that given the divergence and the curl of a vector in a simply connected region, and if you also know the vector field's normal components at the boundaries of the region, then the vector field is uniquely specified. So the Maxwell's equations are going to help you get a unique description of E and B from this theorem, right? So which is why they are so important. So let us consider a vector field. Let's quickly see the proof for this. All right. We consider a vector field. We are given that the divergence is known. We are also given that the curl is known. So let's say that the divergence of K is given by S and the divergence of K is given by C. Okay. So S is a scalar field, C is a vector field, it is a curl of K. K is an arbitrary vector field. We know its divergence and the curl, and we also know the normal components at the boundary of the region. So this is also known. What we have to prove is that if there are two such vector fields, not just one, K and K prime, there is a K, but there is also a K prime. And what is the nature of K prime? K prime also satisfies the same equations. Then you have got a difference vector which is W. What the theorem is telling us is that if K prime also satisfies exactly the same things and has got exactly the same conditions for the normal components, then the difference between K and K prime must vanish, which means that the vector field K is unique. That is the uniqueness theorem. That is what we have to show. So let us determine the divergence of K and of the difference between K and K prime. Since both are solenoidal, both have got the same, both of them have got the same divergence. Okay, both have got the same divergence. We are not saying that it is solenoidal as yet. We have to show that. Then the divergence of this, the difference vector vanishes, right? What about the curl of K? Curl of K is equal to the vector field C. The curl of K prime is also equal to the vector field C, which means that the curl of the difference vector K minus K prime goes to 0, which means that the field W, if not K or K prime, W is definitely solenoidal and W is also irrotational. That is guaranteed. So now you have got W which is both solenoidal and irrotational. And let us consider an irrotational field, and in an irrotational field you write as the gradient of a scalar function, because the curl of a gradient is always 0. Since the curl of a gradient is always 0, you can express this irrotational field as the gradient of a scalar function psi, alright. And the normal components on the boundary of this will be W dot n, which will be the normal component of the difference of the two vector fields K and K prime, and this must vanish, right. So now Let us look at this relationship further, and I am going to invoke this result on the next slide. So, I have marked them with these asterisks. There is a 5-pointed star and a 4-pointed star. So, I am going to use both of these. Okay. So, we also know from vector calculus that if you have two arbitrary scalar fields, then you can take the divergence of the product of one of them with the gradient of the other, and you have got this vector identity. So, the corresponding volume integrals are equal, right, and the volume integral of the divergence of this is nothing but the surface integral, right, that we know from the Gauss's divergence theorem. So, now we have this relation, and F1 and F2 are two arbitrary scalar fields. You are free to choose them to be whatever scalar fields that you wish, as long as they are well behaved scalar fields, and you choose both of them to be psi. Which psi? Which is the same psi that you used earlier, all right. And you use this because nothing stops you from picking it to be that, and you just replace both F1 and F2 by psi, okay. And if you now put W equal to del psi, right, which is that 5-pointed asterisk that we had on the previous slide, then you have the normal component of psi times W perpendicular on the left hand side, and this is equal to these two terms on the right hand side, of which the first term is solenoidal. We have already seen that, because the divergence of W is the divergence of K minus the divergence of K prime, and we took K and K prime to be such that both of them have the same divergence. So, those two cancel each other. So, the first term vanishes. The second term is an integral of W square. It is a sum of W squares, the modulus square of W at every point. So, when the sum of the squares vanishes, the integration is nothing but the sum of the squares. When the sum of the squares vanishes, then the integrand W square itself must vanish, right. So, that will being non-negative. So, W has to go to 0, and that guarantees that K prime is equal to K. That is the uniqueness theorem, right. So, essentially we have proved that if you know the divergence and the curl of a vector field in a simply connected region, and if you know the normal components at the boundary, then the vector field itself is uniquely specified, and that is what makes Maxwell's equations so important, all right. Because from the Maxwell's equations and from the boundary conditions, from the normal components of the boundary conditions, you can get E and B uniquely, and once you know E and B uniquely, you can set up the force equation dP by dt, because dP by dt is force, which is charge times Q into E plus V cross B. You know E, you know B, now you can solve the equation, no problem. Okay? Now you can do electrodynamics using Newtonian ideas. So, this is classical electrodynamics. Thank you very much. If there is any question, we can discuss, otherwise that is it for this class.